First topic. I'm actually going to start with the slide underneath it. Has anybody ever seen The Price is Right and watched the game Plinko? No. Okay, well, if you don't understand this game, let me see if I can explain it to you real quick. The contestant, they walk up to the top of the stairs, they place their little Plinko chip in the top here, and basically the little Plinko chip kind of bounces all the way down and then lands in one of these bins. And if it lands in the 0 bin, you get $0. But like if it happens to bounce and hit the side and ricochet and do whatever it does through here and lands in a money bin, you get that money. Does that make sense? Essentially, this is actually a math problem based on probabilities of the different number of possibilities as to where things would land. But to simplify it, because the Plinko problem is kind of complicated, I want to simplify it back to a smaller grid. Okay. And so imagine this is the Plinko problem, but like tipped sideways. Can you guys envision that in your head where you're going to start... Oh, stupid pen. Heather, could you grab the door, please? You're going to start right here, and we want to finish right here. And the question is, well, how many different paths are there to go from A to B? Don't write this down. I'm just going to start illustrating a few using some colors. So with black, here is a path that would get you from A to B. So 1. Here is a path that would get you from A to B. I'm going to just do a few more. You could go like this. That would get you from A to B.
Or straight.
Or apparently it autocorrects it to straight. Let's use the crayon. You could do this. Here to there, to there, to there, to there. That would get you from A to B. The only rules we have are that you can only go down and to the right. Because otherwise you could do this. You could go like down to here, over to there, back up to here, back over to here, down again, over to here, down to there, up to here, over, back, go back to where you start. Well, that's not really logical because that's crazy. Why would you do that? Also, gravity doesn't work that way if this was Plinko on its side. So let me show you how you actually solve this problem. The basic strategy I want to give you for solving this problem is we're going to put down numbers at every corner and talk about how to reach every corner. Oh my goodness. I'm going to start with the number 1 right here. And the reason why I'm going to start with 1 there is because there's one way to start here, and that's by just starting here. How many ways would there be to reach this corner right here?
Just 1.
And the answer is 1. I could just go just like this. Now I'm going to go down. What if I wanted to go to this corner right here? How many ways could you reach that corner? 1. The answer is 1. Because from here, there's just one way straight down. What about if I wanted to go to this corner right here?
2.
The answer is 2. And if I visualize them, they look like this. I could go right down or down right. Make sense?
So we know the top one.
Ah, good. And that's the next thing we can start to figure out is, well, really, all of the edges are all 1. Because there's only one way to get to this corner, to go straight across. There's only one way to get to this corner, go straight across. Right? And you can actually put 1s down all of the edges. Right? Like if you want to get down to this corner here, the only way to get to this corner is just dropping straight down. Because you're not allowed to go like over here and then back again. Does that make sense so far? Okay, let's try this corner here. How many ways can you get to this corner here? So let me count them out. You can go over and down. You could go halfway down and then the other halfway. And then you could go down and over. So 3 ways. And then here, this is actually 4, which is where some patterns start to get noticed. And I'll count them out for you. All the way over and down is 1. Halfway over and down is 2. Part way over and across is 3. And then down and over is 4. And so then logic would dictate that one's 5. Now if I want to go down this section here, it's actually the same logic here. This will also be a 3 and a 4. I think you guys have these ones already. What was that? Okay, one more, and then I'm going to show you how the pattern works. I want to try to find this guy right here. This one's the hardest one to figure out. Okay. You could go all the way over and down, part way over, like that, part way over, all the way down and over, so that's 3. Then you could go part way down like this, that's 4. all the way down and over was 5, and I think I missed one.
Yeah, one in the middle, you go all the way right and down.
Like
Down
halfway and then
Halfway, all the way over and down, yeah. So this answer is 6. Okay. After a while, you start to figure out that there's actually a pattern to how this works, and it's based on the sum of the two lines that lead to the point. This 3 and this 3, both of these two 3 lines collectively add to give 6.
So the next one over would be like 10.
Perfect. This is a 10 because this 4 and this 6 collectively add to give 10.
So
And then this will be 15 because a 5 and a 10 adds to a 15. 4 and 6 again adds to 10. 10 and 10 adds to 20. And 20 and 15 means there should be 35 total ways of doing this.
Wow.
Okay, I think now's a good time to jump in here. We can actually do this with like perms and comms type stuff we've been working with. Okay. Here's another way of approaching it. If I went like say here down to here, it meant that I would have gone right, 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 and then I would have went down, down, down. So I would have had 4 rights and 3 downs. Does that make sense?
Where did you say that's
So, well, like just I'm considering a path. If I went like here to here to here to here, that's 4 rights, and then down, down, down. Okay. Let me say try a different path though. Let's say I went like let me color it in color so we can clearly see it. We'll use this one. Let's say it was this particular path here. This one would have been down, right, right, down, right, right, down.
Still 3 rights.
But ultimately, wasn't it still
4 right.
4 rights and 3 downs? Okay. Well, we've actually done questions like this kind of before, just not really phrased like this. Really, there are 7 blocks you have to walk total. Regardless of which way you go, for sure you have to walk 7 blocks. But 4 of them are right, and 3 of them are down. And I don't actually care what order this happens in. And that's 35.
Okay, so how come you had 7 factorial?
7 factorial because I have to walk 7 blocks total. I have to walk like 1, 2, 3, 4, 5, 6, 7. I'm always walking 7 blocks.
And then 4 factorial, we could do it 4 right.
Because 4 of them are right and 3 of them are down. I don't actually care what order they go in. I could walk all of my rights first, then all of my downs. I could go like right down, right down, right down. Order doesn't actually seem to matter for me to get there. And so this is another way of solving the question. 7 factorial over 4 and 3.
So if you had like a 4 by 5 block, you'd have to go 9 total, give up over 4 and 5.
Sure, let's try some of these examples here.
Oh, okay. Easy.
So let me try these first by using like number methods, and then we can try it using the new one I showed you. So like along the edges are always 1s. Because there's only one way to go across an edge. Then this 1 and 1 adds to 2. This 1 and 2 adds to 3. This 1 and 3 adds to 4, 5, and 6. Stop me if I'm going too fast. Okay. You're okay? Okay. So then this 3 and 3 add to 6. 4 and 6 to 10. 5 and 10 to 15. And 6 and 15 to 21. On this guy, I got 56.
How did you do that?
Okay, so basically any particular corner is the sum of the 2 lines that make that corner. So for example, this 2 right here is because this 1 and this 1 add to give 2.
So shouldn't it be 1, 2, 3 for the sides? I mean, like on the left side of it, like going down.
Down here, like this should be 1, 2, 3, 4. Because like say this 3 is the sum of a 1 and a 2.
Why
And
is
this,
it 1 though? Shouldn't it be 2?
let me erase it and start from scratch then. All edges are 1s.
Oh, okay.
Like all of these corners right here have to be 1s. Because there's only one way to get to those edges. You could either go straight across to get to this edge right here. That's one way. That's the only way.
Right, it's got
or dropping down is just ones as well. After a while, you kind of catch on to the pattern. By the way, it's kind of symmetrical sometimes, isn't it?
Whoa.
So I got 56 doing it this way. Another way of solving that is to say how many blocks total do you have to walk? You have to walk 1, 2, 3, 4, 5 across and 3 down. So total blocks, you have to walk 8 blocks total. 5 of them are the same as each other, and 3 of them are the same as each other. And hopefully that's also 56.
It is.
Cool. Always. Of course there's a trick. Okay, for this one right here, we could do the whole number method, or maybe a faster way of doing it is saying, well, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 blocks you have to walk. So 10 factorial. 6 of them are to the right, and 4 of them are down.
So for those ones, would you just make 2 separate blocks?
It doesn't quite work all that nicely. You can actually do 2 separate blocks for this one here because of the way that they just meet at one little conjunction point there. But this one right here, since it doesn't really work that way, that formula that I showed you here, the 8 over 5, 3 and the 10 over 6, 4, actually doesn't work for these guys right here. You actually have to do it by counting them out. So let me see if this makes sense. 1, 1, 1 along all the edges. This one and this one add to give 2. This one and this 2 add to give 3. 1 and 2 adds to give 3. And then at this junction right here in the middle, it's 6.
Could you multiply? Do you add them?
Well, there's 6 ways now to get here. There's still 6 ways to get here. Still 6 ways. You know how you were carrying the 1s across? Now you're actually going to carry the 6 across.
Oh dear.
Okay, here's another way of approaching it, by the way. There are 0 ways to get to this location right here because that location doesn't even exist. So then 6 plus 0 would add to 6. And then this 6 and that 0 would add to give 6. So if you really wanted to, you could put zeros there and say they're impossible. But a better way of putting it is just have the 6's carry over. Which means 6 plus 6 is now 12, 18, 24, and 30. I might need some help on the rest of these. That'll be 36. That'll be 60. That'll be 120, 90, 210.
Wait, how would you write that as like the
You can't, because this one doesn't really work that same sort of way, unfortunately.
Wait, so
Well, okay, actually, you probably could do it. You could say that this first little section here, Heather, is 4 blocks total with 2 and 2. And then this section right here was 1, 2, 3, 4, 5, 6, 7 blocks total with 3 and 4. And if you multiply those together, I'm thinking you're going to get 210. You just do it in sections. This one right here, though, doesn't have like a single junction point right here, though. So this guy right here, you have to solve like using just the counting it out method.
how would you do that?
Okay. Let me just make sure everybody's caught up here before I try that one. Any questions on this guy right here? Okay, so then this last one would look like this. 1's around the corners. This would be 2, 3, 4, 3, 4. And that would be 6, 10, and 10. Okay, this is where it gets tricky. For sure, this guy right here is 20. But this guy right here is still 10. Because really there's 0 here,
Okay.
plus 10 is 10. And there's 0 here, plus 10 is 10. And 0 and 0. So the 10s just kind of go around the corner. Giving you 30 and 40. 30, 40, 60, 100, 100, 200.
does it get harder?
Well, the point I need to make today is the combination between this smaller little problem and another problem and how they actually fit together. So, but does that make sense so far? Can I skip this slide? I'm going to come back to this actually. I want to skip this guy right here. And I want to do this next thing instead. So topic 1, seemingly unrelated. Topic 1 is all about like pathways like Plinko. Topic 2, you'd think these things have nothing to do with each other. Okay, this is actually foiling things out. And there is actually a huge similarity between the two. So need you guys to bear with me. I'm going to try foiling some of these things now. Okay, if I were to foil x plus y, which means x plus y twice, you're going to end up with x squared, xy, yx, and y squared. Which means when you're done, you have x squared. You actually have 1x squared. You have 2 xy's, and you have 1 y squared. Does that make sense? Okay. Into that, I'm now going to FOIL this thing another time. So I'm now going to take that answer. I'm going to try to color coordinate this to keep this straight. Into that answer, I'm going to FOIL another x plus y, which is going to give you x to the 3, 2x squared y, y squared x, and you're going to get x squared y, 2xy squared, and y to the 3. Yeah, it actually is pretty nasty by the time we're done. We're only going to do this once to make the point. So I'm just doing the one where it was, this one's going to be purple, and this one's going to be red. Okay, so 2x squared y was by taking this term and timesing by x, which gave me 2x squared y. So I did this one times this one times this one, this one times this one, and then I did this one times that guy, this guy times that guy, this guy times that guy. Okay, let me put it all together. When I'm done, I've got 1x to the 3rd. This guy and this guy can add together. So you actually have 3 x squareds with y. This guy and this guy add together, which gives you 3xy squareds. And then there's 1 y to the cubed. Okay, you're going to see a pattern here after a while. I hope you're going to see it. So now I'm going to multiply this by another x plus y. Okay. By the way, before I move on here, I want to point out maybe some similarities to other questions you've done. There's one question you might have done which has to do with different committees that you can have. Usually it's between, like, you have to have a certain number of men and women on the committee. You guys remember doing questions like that? There's actually a similarity here. Here you have, give me a second. Here you have 3 x's, no y's. Here you have 2 x's, 1 y. Here you have 1 x, 2 y's. And here you have no x's and 1 y. It's kind of like 3 men, no women, 2 men, 1 woman, 1 man, 2 women, and 3 women and no men all together. You see how there's kind of a similarity there?
Basically, that's like choosing a different path, like in formula form.
Kind of, yeah. It's just keeping track of all the possibilities. Okay. Let's FOIL this next one. This one times this one will give you x to the 4. Really, all of these terms here are going to get bumped up by a value of x. So now it'll be x to the 3y. It'll be x to the squared y squared. And this one will actually have an x in it now. So that's timesing all of them by x. Then all of these get times by y, which means that this guy now picks up a y, which gives you x to the 3y. This guy picks up another y, which means it's 3x squared and now y squared. This guy picks up another y, which is 3xy to the 3. And this guy picks up a y, which means now there's 4 of them.
Why didn't the last one pick up a y?
Well, this one did. This one was y to the 3, and then now I made it y to the 4. So this first row is the exact same thing with everyone having an extra x to them. And this guy down here is the exact same thing with everybody having an extra y. So here's what happens when you put them together. You now have x to the 4.
Linda Janzer, can you please call 100? Linda, please call 100.
Now we have this. So I said, well, you have one of these guys. 3 plus 1 adds to 4. 3 plus 3 adds to 6. 1 plus 3 adds to 4, and this guy's just sitting there by himself. One more time, then I promise I'll make my point. I just think I just need one more of these. You're never going to do this again, just so you know. That's not the point of this. Let's times by x plus y one more time. So every term needs an extra x, and then do it again, but with an extra y. So this guy now becomes x to the 5. This becomes x4y. This becomes x3y. This becomes x2y. And this becomes x with my y's. Then all of those terms, I need to write them again, but now I need to add an extra y on all of them. So this guy with an extra y becomes x to the 4y. This guy with an extra y becomes x to the 3y squared. This guy becomes that one. This one becomes 4xy to the 4. And then you also pick up a y to the 5. Final answer. Combine it all up. You're going to have 1 x to the 5. You're going to have 5 x4y, 10 x3y2, also 10 x2y3, 5 x1y4, and 1 y to the 5. Okay. 2 seemingly completely unrelated tasks. Second one of which is kind of really annoying and stupid. Okay. Now I want to try to show you how, I don't know who discovered this. It's absolutely brilliant. Figured out they're related to each other. Okay. Go back here. Take a look at this pattern. You have to look at it diagonally. Come on, pen, work better.
I need to get you new ones.
So no, I need to buy another cord here. Come on. Okay, imagine you have this grid here. Take the grid though, and like shift it sideways so that it looks like this.
What do you mean?
Okay, shift it sideways and look at the numbers. 1, 2, 1. 1, 3, 3, 1.
Oh.
Okay, we're missing it, but 1, 4, 6, 4, 1. Now go back to where I just finished off there. 1, 2, 1. 1, 3, 3, 1. 1, 4, 6, 4, 1. 1, 5, 10, 10, 5, 1.
Oh, so it's like 1, 5.
Okay, take a look at the grid we were drawing here. You gotta tilt it kind of sideways and work on a diagonal. Here, you have 1 and 1. This is like x and this is y. Then you have x squared, 2xy, y squared. This was the 1, 2, 1. 1, 3, 3, 1. 1, 4, 6, 4, 1. 1, 5, 10, 10, 5, 1. Yes, see how these things are actually related? And you would never think that. Okay. I want to introduce to you a concept. I'm guessing it was solved by Pascal. It's called Pascal's triangle. Here's basically how it works. Take that grid we were working with there and actually tilt it though. Oh, thank you, I forgot those. Okay. This is like the edges of your box. So they always have to stay as ones along the edges. Okay. Where did this 2 come from? 1 plus 1 adds to 2. Where does this 3 come from? 2 and 1 add to 3. Like, can you guys visualize how this is working here? This is that same box, but rather than a box, he's made it a triangle. This 3 is from 1 and 2. This 6 is from 3 and 3. Could we figure out the next row in this triangle?
1, 5, 10, 10, 5, 1.
Yeah, this would be a 1 on the edges. 1 and 4 adds to 5. 4 and 6 adds to 10. 6 and 4 adds to 10. 4 and 1 adds to 5. What's your next row?
What's the next?
Like 6 big 1.
So 1's there. Gives you 6, 15, 20,
Oh, I did that backwards.
15, 6.
Oh, so it's like
15, 20.
yeah, I understand. She's really right. Good for him.
Okay. Let me relate this to our next problem here then. I want us to expand this.
Wait, we don't have to.
Yeah, that's the point. So where did we finish off at? We just finished off on the row of 1, 5, 10, 10, 5, 1. So the next row should be 1, 6, 15, 20, and then back down again.
Yeah, but what
Okay, so
How do you
1,
yeah, how do you
okay, bear with me. 1, 6, 15, 20, and
do you
then it would be 15, 6, 1. Now to figure out the terms, all you have to consider is your different options. The first option is that everybody is an X. So that's like 6 men. Then the next is 5 men, 1 woman.
Oh, I see.
Then,
2,
yes. I like hearing those light bulbs going off there.
3, 3.
So the next one would be 4 with 2. The next one will be 3 with 3. Then it's going to be 2 with 4. Then it'll be 1 with 5. And then it'll be all 6.
Huh.
Wait.
6, 5, 4, 2. 6, 5, 4, 2.
So what's happening is your X values are actually dropping. You used to have 6, 5, 4, 3, 2, 1, and 0 X's.
That makes, and then like the 15 and like say the 15 in front of like the X squared Y or whatever kind of thing. That's kind of means like when you're like switching math.
Yeah, because really here you have 5 guys and 4 girls. And here you have, oh my goodness, 4 guys and 2 girls. And here you have 2 guys and 4 girls. You're just flipping them around. But the number in front of it actually stays the same. Here a 1 and 5 ratio is the same as a 5 and 1 ratio. They both get the 6 in front of it.
Well then. Okay.
Okay, one more thing here then. Hope it's my next slide here. It's not. Okay, I gotta go back.
It is new.
Yeah. Okay. Need you guys to help me test some things here. This number right here is 0, choose 0. 0, choose 0 is 1. This number right here is going to be 1, choose 0. And this number right here is going to be 1, choose 1.
What? Why?
Just let me fill this out for a second first. Let me fill it out first, then I can maybe show you in a second. Okay. This is like the 0th row. This is now the first row. I know this is actually like the 3rd row, but I'm going to start off with 2. This is going to be 2, choose 0. This is going to be 2, choose 1. This is going to be 2, choose 2. How's the next row going to work then according to? So 3, 0, 3, 1, 3 with 2, 3 with 3. 4 with 0, 4 with 1, 4 with 2, 4 with 3, 4 with 4. Pascal, I believe, is the guy who's credited with discovering that this triangle here is really actually a choose type scenario here. But it always seems like it's off by 1 because you actually have to start with 0. That makes sense? So this is actually row like 0. This is row 1. This is row 2. Does that make sense? So everything's off by 1 because you have to start with 0. And then same thing along these sides right here. These are always choosing zeros, These are always choosing 1s along a diagonal. These are always choosing 2s along a diagonal.
Brandy
and so
Yellowwings,
on.
can you please come to the office? Brandy Yellowwings, please come to the office.
Let's just do one more just to test this. Okay. This number right here should be 5, choose 0. In your calculators, what is 5, choose 0? Okay. This number here should be 5, choose 1, which should be 5, which makes sense because this 1 and this 4 add to 5. What's 5, choose 2? Kayla, Birdie, can I have your attention, please? Thank you. 5, choose 2 should be 10, which is hopefully from 4 and 6 getting added to each other. Here's where symmetry starts to kick in. 6 and 4 should also add to give 10. So if you do 5, choose 2, it's the same as 5, choose 3, actually. And then this 4 and this 1 should be 5, which is what 5, choose 4 should be. And then over here, this should be 5, choose 5, which hopefully that makes sense. If you have 5 people and then you take all 5 of them, and you don't care what order they're in, there's only one way of doing it. Based on this, we've discovered or found a way to manipulate and create a formula. This formula is crazy looking. Very crazy looking. So let me try to explain what's happening. There are 3 parts to this formula. They're separated by this. Okay. This thing right here is the number in front. This will be like the 1, the 4, 6, 4, 1. You know how we have like a coefficient in front? That's what this will tell us, the number in front. This NCK thing. It'll tell us what number goes in front of our term. Okay. This will tell you how many x's you have. And not x squared, that doesn't really seem proper.
How many components do the x?
I just wanted to go x's. There are supposed to be. And this will tell you how many y's there will be. Well, in terms of how much exponents there's going to be. Let me go back a slide here. Okay. Here's a term. Okay. This term right here is actually 3 different parts. Here is the number in front. Then there were 2 x's. And there were 4 y's. Do you see how there's like 3 pieces of information there? There's a number in front. The number in front actually comes from like, we call it Pascal's triangle. Then there are a certain number of x's you need, and there are a certain number of y's that you need. And so this is a formula that was developed to help you figure out what term you're working with. Okay. But it's kind of confusing because you have n's and k's everywhere. So n is the power of the binomial. For example, on this one right here, what power were we going to? 6. That makes sense? So in this formula here, I would say that all of your n's need to be 6's. Because like in this one right here, n is the power of the binomial. So since this one was to the power of 6, every n that we have here, so this n, they need to be 6's. Okay. X is the first term of the binomial, which was x. It's not always x. Sometimes it's a or b or something else. Y is the second term of the binomial, so that's why I left them as x and y. This is the hardest part to wrap your head around. K is 1 less than the term you want. Because of the way the 0 works. Okay. So like, let's say we're working with this guy right here. Which term is this? This is term 1. This is term 2. Term 3. Term 4. So this is term 5. Makes sense? But if you want term 5, K actually has to be 4. Okay. So then I put a 4 here, I put a 4 here, and I put a 4 here. This is term 4 plus 1, but 4 plus 1 is really going to find you term number 5. Okay, so the 5th term is going to be 6 choose 4. So if you have your calculators, what's 6 choose 4? Okay. Then x will be to the 6 minus 4. So x squared. And then y will just be to the 4. So it'll be y to the 4. And then if I compare this 15x squared y is what I had right here. You need to practice this, like about 5 or 6 times until you get the hang of it. So I'm just going to repeat this to death. Pick another term in here. I don't care which one. Sure, let's do this one right here, the 21. Okay? I want to use this formula to confirm that this is correct. So I just want to go to the other slide here. This is going to be the 1, 2, 3. This is going to be the 4th term. Does that make sense? So let me go back and change all this information here. We're going to look for the 4th term. To find the 4th term, though, k needs to be 3. N is the power of the binomial, so that's what exponent we were trying to FOIL it out to. So still 6, yeah. Then in 6, choose 3 because 3 is 1 less than 4.
Wait, why is it 6?
6 because this exponent up here was 6. I'm going to do it in a second here when we do it with 7. We'll get to that in a bit. Then n is to the power of 6 minus 3, and then y is to the power of 3. So first thing is we need to figure out what 6 choose 3 is because that tells you what your leading coefficient is, 20. Then 6 minus 3 means you have 3 x's and you have 3 y's. What do these two exponents have to add to guaranteed? They have to. Does that make sense? If you're using the men and women type analogy, in this one here, there's 3 men and there's 3 women. It better add up to 6 because it could be 3, 3 or 4, 2 or 5, 1. But those numbers, they have to add up to that same exponent. Okay, let me change this one. Let's go one further. Let's say I asked you to do x plus y to the 7. Just make a blank one here.
So what would we do it for like every single
We could do it for like every single term if we wanted to. Why don't we just pick like one of the terms? So let's just do it for like say the 3rd term. Let's do this for the 3rd term.
So if we're looking for the 3rd term, then k is 2.
Sure. So then if we're looking for term 2 plus 1, which is 3, it goes n, which now will be 7. Choose 2. Then x will be to the power of 7 minus 2, and y will be to the power of 2. So what's 7 choose 2? What's that Pascal's number is going to be? 21? And then you'll have 5 x's, and then if you have 5 x's, by default you must only have 2 y's left. That is the 3rd term in the sequence. Now, if you're asked to actually FOIL the whole thing out, I have a different strategy for you. The strategy would be to do this. Go x to the 7, then go x6, y1. I need a lot of room here. Then go x5, y2. Then you're going to want x4, y3. Then you're going to want x3, y4, x2, y5, x1, y6, and y7. And then all I have to do is figure out the numbers that go in front. This guy is going to be 7 choose 0, which is 1. This guy is going to be 7 choose 1, which will be 7. I need your help with the rest. This guy will be 7 choose 2. Okay. This guy will be 7 choose 3. Thank you. 7 choose 4. Okay, at some point it's symmetrical. So then 7 choose 5 is probably 21 again. 7 choose 6 is back to 7. And 7 choose 7 is back to 1. So if you actually have to FOIL the whole thing out, once you kind of figure out how the pattern works, you just need to recognize that this goes 7, 6, 5, 4, 3, 2, 1, 0 for x. And then it goes the other way for y. And all you need is that Pascal triangle like number in front. Okay, so now let's start throwing in some challenging ones. Okay. Okay, so here's how I do this then. The first one is going to be 2a to the 5, all in brackets. Then you're going to need 2a to the 4 with negative 3b to the 1. Give me a second.
Oh, I get it.
Oh.
Then you're going to want 2a to the 3, but negative 3b is now going to go to the 2. Then you're going to want 2a just to the 2 and negative 3b to the 3. Then you're going to want 2a to the 1 and negative 3b to the 4.
Negative 3.
And then the last one is negative 3b to the 5. In front of all of these numbers, though, we need a coefficient. It's going to be 5, choose something.
0.
The first one is 5, choose 0, so that's a 1. Then it'll be 5, choose 1, which I know is 5. Then it'll be 5, choose 2. 10? Now, I'm guessing 5, choose 3 is the same thing, so it should be 10 again. And then back to 5. And then back to 1.
I love it. So it just looks confusing.
It does. I mean, it looks horrible.
Oh, this next one's more.
Okay, one last thought here, though.
Coach.
If there's only one word.
One last thought. I can actually simplify some of these terms here. This guy can actually be written as 32a to the 5.
Oh.
The reason why is the 2 itself can get multiplied to the 5, which is 32. For this one right here, the next one over. My calculator.
80.
You're going to have 5. Then you have 2 to the 4. And then you also have a negative 3. Guys. And so the coefficient in front of this guy will be negative 240. And you'll have 4 A's and 1 B.
Michelle, would you still put it? If you went 2a to 5, why would you still put the exponent there?
Well, because the 5 applies to the 2, but it also applies to the A. So the A still goes to the 5, but the 2 itself is also to the 5, which is 32.
So you did 2 to the 4 times the 5 and times the negative 3 too.
Yeah. Now, A is still to the 4 and B is still to the 1, but now your leading coefficient is 5 times 2 to the 4 times negative 3.
What does that say? That
Sorry, this is supposed to be negative 240, A to the 4, B to the 1.
negative 2.
Negative 240.
So what do you do? You go, you go 5 times 2.
So I went 5 times 2 to the 4
Yep.
times negative 3 to the 1. Let me do the next one here. On this one right here, in terms of numbers, I have a 10. Then I have a 2 to the 3. And then I have a negative 3 squared. So this one is 720. And then you have A3, B2.
The next one would be this.
So then the next one is 10 times 2 squared times negative 3 to the 3rd, which is negative 1080. And now you have A squared and B3. Next one is 5 times 2 to the 1, so just 2, times negative 3, and that one now goes to the power of 4. So 810. And that's just a single A with B to the 4. And then the last one, 1 is kind of pointless, so just go negative 3 to the 5. And then you got negative 243 B5. So these ones here, they're not, it's not more, well, it's more work. But it's just keeping track of the fact that when you're done, you're not quite done yet. You actually have to take the numbers that are inside those like exponents and actually like square or cube or fourth them, if that makes sense, and put it all together.
Can you simplify even more because they're all huge?
Um,
Or would you just leave it like that?
No, you have to leave it like that then. Okay, let me show you some diploma questions. Let's try this. Actually, how about this? Go take a 5-minute break here. It's been 45 minutes. When you come back, let's do some diploma questions. Let's pause for a bit. Plus my board freaked out again.